Hello everyone, welcome to my video lecture on tutorial uh, problem solving on integration. Most of you are familiar with what integration is. It's just a way of adding slices to find the whole. It can be used to find areas, volumes, central points, and many useful things. So that's we study integration for various reasons. But I just want to come up now with the integration on this integrand a raised minus ax squared plus bx plus c. Obviously, when I teach integration to my beginning calculus students, always I tell them that some integrals are impossible with a bit of expansion to what they actually means. We got encountered certain functions which have no elementary integrals, rather they are presented instead of using special function so that they have no elementary integrals in terms of the standard function. That's all, and well, it's not a big deal. But the question is, how does one obtain an expression for the integral of this non-elementary integral? So this particular example is just an application of integration via completing the square. Okay, because all common integration techniques and even special functions are supported. We have multiple mechanisms to find the integration depending on the integral. We introduce several mechanisms to tackle the integration. So to do this integration, we just want to use integration via complete the square method. Before that, let me remind you just about the Gaussian integral. You remember the Gaussian integration, also known as the Euler-Poisson integral. This integration, we have I from minus infinity to infinity, a raised minus x squared dx. The integral of Gaussian function, e raised minus x squared dx, is the Gaussian function over the entire real line. Thus, no elementary indefinite integral. Had it been the indefinite integral in here, the function has no elementary antiderivative. But the definite integral of this can be calculated. Okay, it's possible to calculate the definite integral of this Gaussian function. Now we assume that I is from minus infinity to infinity, e raised minus x squared dx. Then I square mean from minus infinity to infinity, e raised minus x. Since x is a demi-variable, you can say e raised this I is possibly equivalent with minus infinity to infinity, e raised minus y squared dy. That's possible. Okay, so we have represented with I times I mean, e raised minus x squared from minus infinity to infinity times from minus infinity to infinity, e raised minus y squared dy. So that's the aim is to find the integration of the previous case. Okay, so it helps us with the form of Gaussian integral. This form is useful for calculating expectations. Possibly the Gaussian function, Gaussian integral, useful for calculating expectations of some continuous possibility. Probability distributions with the help of the Gaussian integral related to the normal distribution, okay, such as the log normal distribution. Here we use most of the time the Gaussian integral. So we have I, this just represented for any variable x, so that if had it been y, then true that we get r, because it just assigned for specific value due to the definite integral here. We get the same value if we assign it x in place of xy. It is minus y squared dy is I. So I squared mean the product of the two. This just the duplication of I. That's possible. So I squared mean from minus infinity to infinity, from minus infinity to infinity, then erase minus x squared plus y squared dx dy. Just turn it to the double integral. We sum it up the exponents due to they have the same common base e, so that we just sum it up the exponents. Just sum it up, so we get erase minus x squared plus y squared dx dy. So this is going to be solved via the polar form. We introduce the polar form, polar coordinates. This is the Cartesian coordinate system. Then we just want to use the polar coordinate system using the relation between r and theta. So we have I squared from 0 to 2 pi, from 0 up to infinity. If x is r cos theta, y is r sin theta, then x squared plus y squared is r squared. dA mean r dr, where dA mean the small increment in area, that means dx dy. So instead of dx dy mean r dr, okay, using the Jacobian transformation r dr d theta. That is obviously alright. I think this now is visible. Good. So we use the polar coordinate form, polar form. I squared is from 0 to 2 pi, from 0 up to infinity, where from 0 up to infinity is the r range. Okay, this r range. Again, since x is in between minus infinity and infinity, y is in between minus infinity to infinity, and the previous case. So r in the polar form is from 0 up to infinity. R is a radius, so it cannot be negative. That's why I restrict it to be from 0 up to infinity. Again, the theta angle, because due to we assume the whole xy plane, theta is a 1 rotation from 0 to 2 pi. Okay, that's why we use, instead of from minus infinity to infinity, we use this polar coordinate system from 0 to 2 pi. That is the theta range. Again, the r range is from 0 up to infinity. So we have e minus r squared r dr d theta. Using the substitution, that means we use the polar form. So 0 up to 2 pi, we have to integrate this using substitution, letting r squared is t, dt mean 2r dr, so r dr mean dt over 2. So the back substitution, we get this form. I think it's exceedingly elementary in substitutions here. So that a minus a is r squared over 2 from 0 up to infinity d theta. So at r is infinity, at r is 0, we first complete the computation of r, that is, we assign specific value at infinity as 0. At infinity, as r goes to infinity, this erase r squared is tends to 0. So we have 0 minus at r is 0, we mean r is 0 is half, 1. So my 0 minus half is half, we get half. That's algebraic manipulation. I skip a big chunk of this work due to extremely elementary here in computation using the substitution. So that we get 1 over 2 d theta. Then finally, with respect to theta mean, theta in this case can also be treated as a variable. So integration half is move out, so integration of d theta mean theta. Then you can assign out to theta is 2 pi, theta is 0. So we get this form. I square is half 2 pi minus 0. That means at theta is 2 pi, at theta is 0. With this pair, the vertical pair minus. So 2 pi minus 0. So I square is pi. I square is pi with me. Then square root both sides. So I is square root of pi. Okay. That's why from minus infinity to infinity of a raised minus x squared dx is square root of pi. For any x may be y, x may be u, x may be z, whatever. So for minus infinity to infinity of a raised minus x squared dx is square root of pi. Now let's back to our main case. This is a supplementary to remind you the Gaussian integral, so that our problem is just supported with the Gaussian integral. That's why we need calculating of this form. Now, a raised minus x squared plus bx plus c was our question to integrate this. We first make the completing square method. We use a completing square method. We know that for any quadratic form, ax squared plus bx plus c, we have this form. For any x squared plus bx plus c, we have a into x plus b over 2a squared plus c minus b squared over 4a. Due to this, we have, in this case, this is minus a. Instead of a, we have minus a. So we use minus of x plus b over 2a. Here a is minus a in our case. We need to associate with our form for simplicity. Then c minus b squared over 4a mean a in this case is minus. So just intuitively let's have this form. Okay, using the complete square method, we get from minus infinity to infinity, and instead of this form, we have this form. Okay, here is minus a x minus b over 2a squared plus b squared over 4a plus c. The expression, equivalent expression, we just want to be represented for convenient via the completing square method. We just complete the square to have this form. Now this can be rewrite as areas here using the exponential property of exponential function, areas minus x minus b over 2a squared times areas of b squared over 4a plus c dx. Now areas b squared over 4a plus c is free of x, so that it can be regarded as or treated as constant with respect to x, so that we can use as a constant multiple rule, move out of the integration, out of the game of integration. So it becomes this. If you move out of the integration due to a constant, we get this form. So we have a b squared over 4a plus c from minus infinity to infinity, a raised minus x minus b over 2a squared dx. Now we look at here the integration, a raised minus of ax minus b over 2a squared dx. So letting u is square root of a, we have square root of a x minus b over 2a, then making differentiation both sides respect to x, we get dx is du over square root of a. Therefore, instead of dx in our integral, we use du over square root of a. So if you use if u is square root of ax minus ba over 2a, then u square mean a of this. Okay, u square is this is u square, this is u square excluding of the minus. So this downwards, a raised b square over 4a plus side, it is minus infinity to infinity. We have a raised minus, this belongs to u, so u square, then dx mean from the previous substitution is du over square root of a. Therefore, we have 1 over square root of a raised b square over 4a plus c. Then we have just moved out square root of a, 1 over square root of a as a constant. That's what we move out. Okay, we have this using substitution. We got an expression a is minus u square du over square root of a. 1 over square root of a is a constant, so we move out of the integration, then it becomes here. So we have a raised b square over a plus c. Then this integration is reduces to have a raised minus u square du. Essentially, we got this form, because you remember from the previous of Gaussian integral, for any e raised minus x squared dx is square root of pi, square root of pi. For any from minus infinity to infinity of e raised minus x squared dx, we have the same, just a matter of substitution. If u is x, we mean from minus infinity to infinity, e raised minus x squared dx is square root of pi. From minus infinity to infinity, e raised minus y squared dy is again square root of pi. Just a representation from the previous. The Gaussian integral represents for all variables x. So we get e raised b square 4 plus c. This is e raised b square over 4a plus c over square root of a. So this is square root of pi. So that I use square root of pi only. Okay, this was resulted from the Gaussian integral. That's why we just derive the formula of from minus infinity to infinity e raised minus x squared dx. So finally we have e raised b square over 4a plus c, then square root of pi, square root of a, then square root of pi over a common. So that from minus infinity to infinity of a raised minus x squared plus bx plus c dx is square root of pi over a raised b squared over 4a plus c. The arbitrary Gaussian function here, for arbitrary Gaussian function, so this is the general formula for any an exponential function with the quadratic form. This we use a complete square method. It's a really interesting case in finding integration of similar functions in such form. Then we usually use the complete square method. So if this is the general form, we specifically obtain integration of e raised minus x squared plus 2x plus 1. You just want to be plugging inside this formula that we have already obtained here. So that is just pretty easy to understand. Whichever you're plugging inside here, we have a formula that it has its own formula. It's a formula, solution. Let's say if a is 1, b is 0, c is 1. Let's say if a is 1, we mean b is 0. From minus infinity to infinity, e raised minus x squared dx means square root of pi over 1. That is square root of pi as we expected from the Gaussian integral. Okay, so it's just a general formula. It just sounds easy, again interesting. So to bear in mind, from minus infinity to infinity over the real line of the exponential with the power of quadratic form, we have square root of pi over a raised b squared over 4a plus c. Say if b is 2 in this case, then a is 1, c is 0. We have square root of pi over a, a is 1 already, square root of pi, e raised 2 squared is 4, then 4 over 4 is 1, so e raised 1 is e plus c, because c is 0, so e square root of pi times e we mean. That's extremely elementary after you have been derived. Okay, after we have been derived, unless it is just complicated in making integration. That's why we have used it as support of Gaussian function e raised minus b, e raised minus x squared dx over the real line, so that we can find the integrations of another function similar with the quadratic form with the same function. So integration by completing square helps us with when quadratic functions are involved in the integrand. If you have encountered quadratic functions which are involved under the integrand, then it's just recommended to use the completing the square or complete square method is essentially necessary to do the integration. So we have just used integration via complete the square method on our problem for this. So do not forget to subscribe this channel to get similar working problems, either integration or any calculus or any relating with the mathematics, which are offered in higher institutions. Okay, so have a nice time. Subscribe the BK Maths YouTube channel to get the same problems. Bye.